Okay, let's begin with the first exercise. So the first step in modeling the performance or the power output of a PV system is to model or determine or measure the inputs of the system. The most important input for a PV system is the irradiance. Now there's different types of irradiance. We have the global components. As irradiance travels through the atmosphere, some of it scatters, and this will become diffused irradiance. That's why when you have a cloudy day, you can still see light. The light that you see, that one is diffused irradiance, and the diffused irradiance comes from all directions. If you have a sunny day and you can see the sun directly, there are parallel rays coming from the sun reaching you. That's the direct irradiance. And then there's a third type of irradiance. It's the direct and diffused irradiance that reaches the ground, and some of it is reflected. How much is reflected? It really depends on the surface or the reflectivity of the ground. So for on any object at any point in time, the irradiance that reaches that object is made of kind of these three components. Now these three components, the direct, diffused, and reflected, kind of make together the global components. And we can measure these using some very specialized equipment. We can measure at least two of them. We can measure the direct radiation with something called a pyrheliometer, and we call this direct irradiation the direct normal irradiance because it's normal to the sun's rays are normal to the surface that we are measuring them. So basically we have a 90-degree angle between the surface of measurements and the sun's rays. Then we have something called diffuse horizontal, because depending on the surface or the tilt and orientation of the surface, you see a slightly different irradiation. The standard for kind of characterizing and measuring irradiance is in the horizontal surface, because you can determine a horizontal surface at any place, and then it allows you to do comparison how much solar I have here versus in another country. And the third component is kind of the sum of these two. It is the global horizontal irradiance. So whenever you find a solar resource map, or if you are comparing the solar resource in two locations, you are usually comparing it in the horizontal plane, because this is the standard for measuring and reporting irradiance. However, most often we do not install panels in the horizontal plane, we install them at a tilt. Now, for you guys in Réunion, you are very close to the equator, so you are actually closer to the horizontal for your optimal tilt. But here in Denmark, the optimal tilt for panels is around 39 degrees. So that's where we get most of our energy. So depending on where on the globe you are, you'll have a different optimal tilt, which gets the most irradiance, and you'll also have a different azimuth, so orientation. Is it south? Is it north? Is it east? Now, the plane of array irradiance is the irradiance that actually reaches the surface of the panels. So if your panels are tilted, the irradiance that reaches the panels is slightly different than the global horizontal irradiance that reaches the horizontal surface. So this is the input that we need to calculate for our models, is the plane of array irradiance, which we call POA, and is made also of three components, very similarly to these three components here. There's a direct component for which we just need to know some angle equations to calculate it. There's a diffuse component, which is calculated directly from the diffuse irradiance. And it's because, when you have a horizontal surface, you see the whole sky. But if you have a tilted surface, you only see part of the sky. So, yeah. And then the last one, you also have a reflected component. And especially when you have high tilt angles, the reflected component starts to become more important. When you are close to the equator and your tilt is very low, there's not a lot of reflected light. But if you have, for example, building integrated solar panels that are at 90 degrees, the reflected can be more significant. So the first exercise will be how do we calculate these three components? And we calculate them from the solar resource. This is what you can get from meteo services such as PVGIS, MeteoNorm. You get the solar components. This is also what the weather stations measure. And like one of these weather stations, like you also have on the campus, these are super expensive. They are difficult to maintain, but they are kind of the benchmark of measuring solar resource, because once we have these, we can calculate the irradiance for any plane. So they are very valuable, but they require kind of this tracking system that follows the sun such that it's able to measure the direct component, the diffused, and the global horizontal. So this is a tracker. This is the one that you have on the campus, and all the, let's say, meteo labs have something like this for measuring the components. Now, there is a way to measure the plane of our irradiance directly, which is cheaper, and that is using sensors that are installed in plane with the panels. And then the sensors can be small cells, which are called reference cells, or they can be pyranometers like this. It's just that pyranometers usually are 5 times more expensive than something like this. Now, these are very nice and they are useful for getting the input energy of the panel. The only disadvantage is getting from plane of array irradiance at some orientation to another orientation is difficult and is not very accurate. So you can only use these measurements for this plane of array. If you want to use these measurements for another plane of array, they are basically not useful for that. You will need to have the components. That's why these are so valuable. But it is possible to measure the plane of array irradiance. And in the data set that you receive in this exercise, you'll also have some plane of array irradiance that was measured. So how do we get from these components here to the plane of array irradiance? We use some geometrical equations. First, we need to know the position of the sun, right? Because at any point in time, the panel is fixed, but the sun moves. So how much diffused and direct irradiance you get, especially for how much direct beam irradiance you get in that plane, depends on where is the sun and what is the angle between the sun and the surface of your panels. And that angle between the sun and the surface of the panel we call the angle of incidence. And this angle of incidence depends, of course, on the tilt of the panels, but also on the position of the sun in the sky. And the way that we characterize or measure or model the position of the sun in the sky is with solar angles. We have a solar zenith and a solar azimuth. The solar zenith basically tells you the height of the sun in the sky, and the azimuth, it tells you the cardinal direction. Now, these angles you calculate from a solar position model, which we'll not go into today. There's several ones, some are more accurate. There's quite some complicated equations, but you can, in principle, for a location and a given point in time, you can calculate using one of these solar position models where it should be in the sky. For today, we'll just assume that we solve that one, and we'll use a solar position model that is implemented in pvlib. And if you want to learn more about that, you can just click the link here, and it will lead you to this pvlib website where there's actually a lot of different models for calculating the solar position, but all of them do the same thing. They calculate the sun's zenith and the sun's azimuth. And then if you know these two, you can calculate the angle of incidence at any point in time for a location and a PV array. Once you know the angle of incidence, it becomes a geometrical kind of equation to calculate these three components. So the beam irradiance would be calculated from the angle of incidence and the direct normal component. The diffused assumes a isotropic or a uniform kind of sky, diffuse light from all directions, and basically then you have half a sphere, and then you are calculating how much area of that half sphere are you actually seeing, and then multiplying with the diffused horizontal irradiance, which sees the full sphere. So this is a view sky factor kind of model. And then finally, for the reflected irradiance, it's very similar to the diffuse. So how much of the ground does the panel see? And this will depend only on the tilt of the ground. And then you multiply that with the reflectivity of the ground, which you call albedo, and with the global horizontal irradiance. Now, because we will work with very low tilts, this will be very close to zero. So you can almost ignore it. It becomes more significant when you have higher tilts. Okay. So our first task will be to calculate the plane of array irradiance for these two roofs. So for the Enerpus building, we have two roofs, which have, each of them have a slope or a tilt of 9 degrees, but they are oriented differently. One is 14 degrees northeast, one is opposite of that. And then for this location, we also know the GPS coordinates. We, as inputs for the models, we have some weather data acquired from this weather station from 2 weeks in October 2022. So we'll use that as an input. To validate our model and see that we've made the calculations correctly, we have measured plane of array irradiance measured with these two sensors. So what we'll do, we'll take the weather data, we'll apply our models, we'll get some plane of array irradiance, model plane of array irradiance, and then compare it with the measured one, and we see how close we are to reality. So we'll take it step by step. And I think for the first exercise, I will guide you through most of it, just to get some inertia. So if you've managed to open this exercise and you are at this point here, you will see this small play button. When you play this, it will ask you something. This notebook was not authored by Google. That's fine. Run anyway. And then you'll see a little bit. It's thinking, and then something is happening. So right now you have this virtual machine located in the cloud, and it is installing a number of Python packages. So Python is just a programming language, and then it's made of a lot of libraries that you can install at will. And the libraries that we'll use today is Pandas, NumPy, and the most important one is pvlib. pvlib is a community-driven library for modeling all aspects of a solar photovoltaic system, from irradiance to panels to inverters to trackers and so on. It's very big. We'll learn how to use some of the equations, some of the functions there. So what this, after you run it, you'll see here a small check mark, and then you should see something like this. Successfully installed pvlib 0104. That means all the libraries that you need are loaded, and now you can use pvlib functions. If this is not successful, anything else will not run from here on out. Okay, so our first step in the task is to initialize and load basically the libraries. If this is successful, usually the second part will be to initialize some variables. So what do we know about the system? We know the tilt and we know the azimuth for the two roofs. We also know the location and we know the time zone. And this will be whenever we work with time variables, we need to localize them to the time zone where they are. And then we have also 3 data sets that were provided by Mathieu and which were required at the Enterprise building and at the campus. We have a weather data file, and you can actually just download it after the course, after the workshop. You can inspect these, download them, and use them in your exercises and research if you want. So the first one is just a weather data set, which I'll go a bit when we get to it. The second one contains both plane of array, PV power, and inverter power measurements from the Enterprise building. Both of these are just for 2 weeks in October. So these kind of 2 data sets go together. The third data set is a data set for 2 years actually, which will only extract 1 year. So it's a larger data set that we'll use at the end. So right now we are just initializing the path to these data sets. The 3 data sets are hosted on this GitHub repo that you can inspect afterwards if you like. So let's have a look at the first data set, the Meteo Terrasan. This is kind of the name of the weather station they have there, and it's measured in 2022 between 1st and 15th of October with a time step of 10 minutes. If you actually download, open the file, you'll see that it has 10 columns. First is time, then you have the 3 irradiance components, and then you have some other weather measurements that are not necessary for this exercise. So we've loaded the variables. We have a green check mark here. Now we can go and also load the irradiance data set. And we load it using pandas and this read CSV function, which basically will take the comma separated file and run it. And then we do a little bit of renaming variables just to make things a bit easier. So we have kind of the inputs to our model loaded. Now the next step is to calculate the solar position for this location and this period of time of 1st to 15th of October 2022. And we'll use some pvlib functions that you can read more about by clicking on these links. They will bring you to the API documentation, which will explain a little bit the parameters and what they do. So the first one is just a location object, which is used by the solar position model. And the second one, the get solar position, has the solar path or solar position model implemented in it, or one of them. And what you need to provide to it is, of course, the location and the time. And the time needs to be localized it needs to be local time, not CET or things like this. So it needs to be localized to Réunion. If you run it, this will plot the solar azimuth and the solar zenith angle. And then you can see that the solar zenith angle varies between 0 and 150, and the solar azimuth basically makes a circle in the sky. And then you can see on the x-axis, you have these 2 weeks of data. So if you get something like this, then you are on the right path. So now we basically have, in this solar position angle, you will have a zenith and an azimuth column. This is a pandas data set, which looks something like this. Solar position dot head and in this data set, you have the date time. So for each 10 minutes in the data set, and then you have a number of columns. And the ones that are of interest to you are the solar zenith and the solar azimuth. And we'll use this further. So basically in our equations here, we have the theta z and the theta a. These we've calculated from the location and the time. Now we'll need to calculate the angle of incidence. we know the tilt and we know the azimuth of the array. So we could in principle just write this equation and then use the arc cosinus to calculate it. Or we can use one of the functions that already do this in pvlib. So one of the functions that already does this is the irradiance.aoi. Let me see. No. Okay, I have the wrong link here. You can just Google it, irradiance.aoi, and you get to the same thing. And basically, this one calculates the angle of incidence on a surface. And you need to specify what is the surface tilt and azimuth. This is the panel, and you also need to give it the solar zenith and the solar azimuth. And this is what happens here. We say solar tilt is the array tilt, surface azimuth is the array azimuth, and then we make a distinction with NE and means northeast and southwest between these two. And then we give it the solar azimuth equals with the solar position azimuth and the zenith. And then because we have two surfaces, we calculate what is the angle of incidence for both, and then we plot them. Let's see what we get. So when we plot these two, we can see that there's the two surfaces see different angles just because of how they are oriented. Okay, so now we are basically here in our equation. So now what we need to do is implement these three equations one by one. So we'll start with the beam irradiance. And I will do this one for you. Let me see where I have it here. So how do we calculate the beam irradiance? Well, we have the AOI, and we have the let me explain it here. So first, we basically just initialize the beam irradiance vector with zeros. And then for angles, because we only want to do the calculations when the angle of incidence is below 90. If it's above 90, it means it's under the panel, so the suns are set. So there's no point of applying these equations because we would get some strange values. So first we set the beam irradiance array with 0. And then for those angles that are below 90 degrees, then we apply equation 3. And equation 3 says you need to multiply the DNI with the cosinus of the angle of incidence. And this is what we're doing here. The DNI we can get from the weather data set. We say weather October 2022, and then we use this kind of addressing for pandas column. And we select also all the or this kind of we do a selection of only those rows that correspond to an angle of incidence below 90. And then we multiply with cosinus of the angle of incidence. And the angle of incidence that we've calculated here is in degrees, and the cosinus wants to have radians. So we use the radiance functions to convert the degrees to radians. And in this way, we've calculated the beam irradiance for the northeast. To do it for the southeast, we do kind of the same thing. We just use the angle of incidence for the southeast angle. Okay. Southeast. And when we run this, we get, well, here it should say the beam irradiance. Beam irradiance. And then we can see that roof northeast sees more beam irradiance than the southwest. And why is that? It's because Réunion is located below the equator. So the optimal orientation for the southern hemisphere is actually north. So you guys need to orient your panels north typically to get the most irradiance, whereas here in Denmark, we need to orient them south. And here we can see actually numbers that the panels that oriented north see slightly more irradiance, in this case beam irradiance, than the ones oriented south. Now next we need to implement the other two equations. So equation 4 for the diffuse irradiance and equation 5 for the ground irradiance. And let me see how we are on time. Here. Yeah, I think I will finish this exercise and the demo with you, and then I'll let you do task B. So we'll need to implement in a similar way the diffuse component and the ground-based component in step 7. And those two, let me see where those are, look something like this. And we can do it in two different ways. We can implement the equation. So dhi times 1 plus cosinus of radiance and the rate tilt. So exactly the equation that we have in equation 4. Or we could use a pvlib function that does exactly the same thing. And the pvlib function that does exactly the same thing is called irradiance.isotropic, and then you give it the surface and the surface tilt and the dhi, and then it implements exactly the same equation. Now for the ground diffuse irradiance, we have similar thing, a very similar equation, but we have GHI instead of DHI, and then we have this ground reflectivity. And then this ground reflectivity depends on the type of surface that that you have there. I think I'm a bit too far away. And for an urban environment, the ground reflectivity is around 18% or 0.18. So how to implement this? Very similarly, either by implementing the equations like this. So GHI times albedo 1 minus cosinus of the tilt, or there is a pvlib function called get ground diffused, where you give it the tilt and the GSI, and you specify the surface. And if you go to the help for this one, let's see if we can find it. You have different types of surfaces here: urban, grass, fresh grass, snow, which have different reflectivity types. So you'll need to change this if you are modeling for different types of surface. But as I said, since the tilt is so low, this doesn't make that much of a difference. It would be make more difference for a higher tilt system. So run this, and then we see what we get. We have, this is only for the northeast side, and we can see for different days, we have kind of a different distribution of the beam and the diffuse. So if it's a very clear sky day, there's no clouds, most of the irradiance is beam irradiance. And since there's no clouds, there's not a lot of scattered irradiance. When you have a cloudy day, the beam irradiance is scattered in the clouds and becomes diffused irradiance. So the part of the diffuse components becomes larger for overcast days or partly cloudy days. And this is also what makes forecasting of solar irradiance so difficult, or calculating from satellite measurements like these clouds make it very difficult to actually know what is the irradiance on the ground. Whereas for the reflected one is almost zero, so it's we can even ignore it for this system. Now we have the three components. All we need to do is add them up. So we can add them up like this. So we, for each of them, we have the plane of array of the northeast system will be the sum of the beam, the sky diffused, and the ground. And then in order to visualize it, it's a bit easier if you just choose a day that is a clear sky day. This will make comparing variables a bit easier. So we'll choose the day of 9th of October, and then we'll only plot that day from the data set. And then we have the plane of array irradiance for the northeast roof, for the southwest roof, and we have also the horizontal irradiance. And we can see actually that for this particular day, the horizontal surface is actually getting more irradiance than these two tilted surfaces. And between the two tilted surfaces is the one that is oriented north that gets more irradiance. Of course, this will change throughout the year depending on the relative position of the sun. So here you can see kind of the differences between, this is what a solar station would give you, the GSI, and what the panels receive. Now, the last step would be to see, okay, how well did we do with our modeling? Just make sure my sound works. Okay. How well did we do with our modeling? And for that, we'll use the second data set that was acquired directly from the NRPOS building and those two reference cells that I showed you. Now, this data set is also acquired from the same period with a time step of 10 minutes. And then it has a lot of variables. But the ones that are important now, it has the timestamp, and then it has the measured plane of array with those two sensors for the northeast and the southeast. So we can load this one and then compare it to what we measured. It also has the DC and AC power measurements that we'll use in the next exercises. So we'll load this exercise into a second data frame that we'll call PV measurement October 2022. And we just run the cell and we get a check mark. And now we will compare the simulated with the measured irradiance and see what we get. And we should get something like this. So we see, for example, for the northeast is the blue, and the measured northeast is the orange. So there is a slight difference between what we modeled and what we measured. Similarly here, Now, the difference can be from different reasons. One can be that the sensor is not calibrated well, or as the sensors age, the calibration drifts, or as you can see here, even though there is a difference, they also seem to be a bit shifted. And what I understand from Mathieu, that these sensors are not exactly installed in the plane of array as the panels, or as stated in the data sheet of the system, and you can kind of see it here. So even like small angle variations in the placement of your sensors or in the measurement of the tilt of the system can lead to some inconsistencies. But we can trust our models because especially since we use pvlib functions, and we didn't make, or especially the easiest to make a mistake is in the solar position model, but there we use the pvlib functions. So you can use sometimes the model to verify if your sensor is correct. Most often you use the sensor to verify if the model is correct. So here we see some inconsistencies, and on further discussion with Mathieu, this was because these sensors are not exactly, were not, for this period, were not installed at the right tilt, but they give us at least some confidence that we are within the ballpark of the measurements. So this is, let's say, the difficult way to model plane of array irradiance by implementing these equations. Now, the value of the equations is for you just to understand how this is done. In practice, you typically don't need to use the equations or implement them, because somebody has probably implemented them for you. And this is also true of pvlib. So instead of using the equations, you can use a function called get irradiance total, which does exactly the same thing. Determine total in-plane irradiance as well as its components using a specific sky diffuse model, which in our case will be the isotropic one. So it's going to be a single function that does all the steps that we did. We need to give the function a tilt, an azimuth of the panels, as well as the zenith and azimuth of the sun. So this data frame that we calculated with the solar position model, we still need to do that and provide it as a parameter. And then we also need to give it the weather measurements. So all the inputs that we use, we still need those inputs. It's just the three equations. This function implements the three equations and the AOI calculations inside of it, and basically does the same thing. So we can maybe even comment this one. Cancel. And then if we compare the model simulated with the equations with the ones with pvlib, they coincide with each other. So the get total irradiance functions does what the equations, or implements the same equations. But it's important for you to know at least what's in those equations, so it's not a black box. So this is how you would do it with just using some of the pvlib functions if you are aware of them. Okay, let's see how we are on time. We are, let's see here. So we'll go up until 12:30, and then we'll have a short quiz. So I'll introduce the second task, which I will let you do it. Which the second task will be to calculate the plane of array irradiance using the functions that you've seen so far, but not for 2 weeks, for the entire year of 2022. And then I will also like you to, because we don't have plane of array measurements for 2022, I would like you to validate using PVGIS. And maybe some of you are familiar with PVGIS. PVGIS is a free solar calculator and solar database tool created by the European Union or European Commission that you can use freely to get solar irradiance and weather data from almost anywhere in the world. And the way it works, you need just to provide it with the latitude and longitude. In this case, you have it there. And you can do a lot of things. The things that I'll want you to do is to simulate what is the irradiance for the slope and the azimuth of these two roofs here, and compare with the measurements that you got or the models that you got. Now, PVGIS doesn't use the same weather data as input. It uses a different data sets, and we'll talk about that when we get there. So what you need to do in task B, apply exactly the same modeling procedure, but instead for 2 weeks, do it for the entire year of 2022. And here you have a second data set from the same weather station, which contains actually 2 years of data, but we'll only use the 2022. So here we are kind of limited to 2022. So if you run this one, you will load the data set. And then from here on out, from step 2, I will leave it to you guys. And then we will, I'll give you 20 minutes to work on this, and then we'll shortly discuss the solution. And then we'll take a very short quiz and then a break. That's the plan. So I will give you 20 minutes to do the rest from step 2 to step 6. So if you have questions, me and Mathieu will be in the chat. So start with step 2.